My name is Ashwin Deshpande, and I worked with Leslie Kaubling and Tomas Lozano Perez. And if we think about robotic planners, all the practical implementations fall into either being sample-based and or resolution-based. And those algorithms are very fast, but unfortunately, they don't have strong theoretical guarantees. Sample-based planners can never determine if a solution does not exist, and resolution-based planners are always somewhere on the spectrum of incorrectness to incompleteness. So if you want to be more theoretically sound, we have to look for decision procedures, like those of Shorst and Scherer and Canny. And these are much more theoretically sound, but they're very slow. So everything today is of theoretic insight, but doesn't really have any practical value as of yet. So a decision procedure is an algorithm for a robotic planning problem that in bounded time will either return a proof that a solution exists or a proof that a solution does not exist. And we're interested in focusing on prehensile task and motion planning, or PTAMP. So what is PTAMP? Well, we start off with a bunch of robots. We have a bunch of movable objects. We have some obstacles. And we have two modalities of moving around. We have transit operations in which the robots can move around. And we have transfer operations in which the robots manipulate objects. So this is very similar to navigation among movable obstacles, manipulation planning, pick and place planning. It's been done many times before, and this is essentially the same thing. We just want to make sure that we're clear that the object manipulations are prehensile. So this has been around for decades. So what are some of the decidability results we have for this problem? Well, there's generally two camps of results. The first is when we assume that we have discrete grasps and placements. And we can get some very strong results for this. We can show that the problem is decidable with multiple robots, multiple objects, high-dimensional spaces, and complex geometries and dynamics. The only problem is that we have to pick all the graphs and placements a priori, which is tough. If we assume we have continuous graphs and placements, then the planner does that job for us, which is great. But the results are a little bit weaker in this case because all the existing results can handle a single robot, at most two objects, generally in a two-dimensional space with very simple geometries and just translations for dynamics. So the result we'll present today is, again, operates in the space of continuous grasps and placements, but it can extend to multiple robots, multiple objects in high-dimensional configuration spaces with semi-algebraic geometries and dynamics that are characterized by polynomials. So that covers translations and rotations, but also some non-standard dynamics, such as twisting or morphing from one shape to another. And in fact, we can go beyond that result by allowing obstacles to be local to specific objects or operators, such as only light objects can traverse a poorly constructed bridge. So how do we get this result? Well, let's start off with the framework. We start with the configuration space. And this is a joint configuration space of all the robots and objects together. We assume that there's a Euclidean coordinate system over this configuration space, which we utilize quite a bit. And to move around this configuration space, we have a set of operators, and this consists of a set of free dimensions and a predicate for each operator. So the free dimensions are just the dimensions that can be modified by the operator. So in a transit operation, the set of free dimensions are the configuration dimensions of the robot that's moving. And for a transfer operation, it would be the configuration dimensions of both the robot and the object involved. Now, all the other dimensions are held constant throughout the execution of the operator. And so this induces a foliation over a configuration space in which each leaf of the foliation corresponds to a maximal potential reachability set for an instance of an operator. In addition, every operator has a predicate, and the predicate specifies when the operator is legal. So for a transit operation, we just don't want any robots, objects, and obstacles to collide with each other. So for the one-dimensional PTAMP case, we get the two triangles as the predicate. For a transfer operation, we may want the additional constraint that the robot and the object have to be touching during the manipulation, in which case we get two one-dimensional lines. And the interesting thing is that the predicates actually describe all the geometric properties of the domain. There's no additional structures needed. And we really prefer when the predicates are open, because that makes our life easier, as we'll see later on. But that's not always possible, like in the picture shown. So to tie these two concepts together, we have semi-holonomic controllability. So if we start off with a predicate on the left and a foliation over the configuration space defined by our free dimensions on the right, we pick a leaf of that foliation and intersect it with our predicate. And within that intersected space, we can move around holonomically. And this is sort of an interesting formulation for the problem because we completely integrate out time. And our entire framework just focuses on reachability. So how do we get our decision procedure? Well, it's a three-step process. We first decompose the configuration space consisting of all the predicates into a finite number of manifolds. We calculate the controllability, or which directions we can travel within each of those manifolds. And then we perform a graph search over those manifolds to determine the total reachability set. So our decomposition procedure relies on the fact that the free dimensions of our operators are Euclidean axes. And so if we want to calculate the controllabilities of these manifolds, it's very convenient to decompose them along the Euclidean axes as well. So our decomposition procedure is actually to utilize cylindrical algebraic decomposition in every decomposition ordering and intersect the results. And we actually have to do it twice to get all the properties we need. So it's a pretty messy decomposition, but we'll see why we need it in the next steps. So then we want to calculate the controllability within each manifold. So if we have a manifold as shown on the bottom, and we have two operators, one that allows for horizontal movement and one that allows for vertical movement, by utilizing the Czartoryski theorem, we know that a finite number of interleavings of these operators will allow us to traverse between any pair of points. However, if we have a one-dimensional manifold, even if we have those two operators, we still can't get between any 2 points in the 2D plane. In the first case, there's not enough room to utilize to interleave those operators. And in the second case, we have a sort of a non-uniform manifold where we can travel horizontally on the left side, but we can't on the right side. So we want to get these nice uniform manifolds. And a single iteration of cylindrical algebraic decomposition in every decomposition order guarantees that we get uniformness with respect to the alignment, with respect to the Euclidean axes. And when we end up with another foliation of each manifold into a bunch of leaves, where each leaf corresponds to a reachability set of the manifold. But there's another way to move around, which is stratified controllability. So if we're in the region M, maybe we want to maybe we can only manipulate the robot in M, so we can travel horizontally. In the region M, we can move around the robot as well as manipulate the object. So we can move from M horizontally over to N, and then in N manipulate the object as well, in essence moving vertically, and then move the robot back to M. So while the robot didn't change positions, it effectively manipulated the object. And so we want to be able to account for that kind of controllability. And to do that, we need to make sure that if we can get from M to N across one of those transit paths, we can get back along another transit path. So we want to get uniformity of those operations. So in order to guarantee that we get uniformity, we have to perform cylindrical algebraic decomposition on our original configuration space twice. But there's still another issue, which is, well, what if the geometry of one of the manifolds that we can reach does not allow us to internally travel in the direction we want? So we want to be able to travel vertically in the manifold N to get vertical stratified controllability for M. But N is one-dimensional and can't utilize the operator that is available to it. Well, it can use stratified controllability itself to be able to travel vertically. But the only issue with that is that we may have to go an infinite number of steps, and each of those steps corresponds to decomposition, and we get an infinite decomposition, which is a pain. So we assume that we have the convergence condition. The convergence condition states that if we have a manifold and it has an operator that can move in some direction, like the vertical direction for N, then there's some way to move vertically in N, either internally or via stratified controllability. We don't quite know how that's done, but we assume that it's true. So that's a great property to have, but what domains have that property? Well, if every predicate is open, which is why we prefer when the predicates are open, then the problem instance does satisfy the convergence condition. The problem is that PTAMP is not open. As we saw before, the touching restriction introduces codimension 1. So our solution is a perturbation technique where we thicken each low-dimensional manifold and make it full-dimensional, as shown in the picture. And the question is that relevant? Is that semantically relevant to the problem we're interested in? Well, in physical systems, we assume that there's always a little bit of gap. The robot never exactly fits into a hole. And we exploit that gap by fattening these manifolds. So it does make physical sense, semantic sense on physical systems. So in terms of calculating our reachability, we have all our various control abilities. So we start off in our initial state and perform a graph search. And once we reach a manifold, we never have to revisit it because we've already calculated the closure of its control abilities. So after one pass of graph search, we've calculated the entire reachability set. And then we take the goal region and intersect it versus that reachability set and test for emptiness. So the problem is very easy, apparently. Or is it? It's not. The time complexity is at least doubly exponential. Cylindrical algebraic decomposition is doubly exponential, and we use that an exponential number of times. So yeah, don't think about implementing this anytime soon. But in terms of future work, we want to calculate an upper bound on the perturbation magnitude, not just say that if it's small enough, it'll work. And we also want to extend the idea to systems that are non-semi-holonomic, like robots pushing objects. So in summary, we codified a semi-holonomic planning framework. We showed that open domains in this framework are decidable. Any domain can be perturbed to become open. And PTAMP can be perturbed with minimal semantic changes because it's a physical system. And putting those three together, we can conclude that PTAMP is decidable. So any questions?
Thank you. Thank you. Jory is our first responder. Okay. Yeah, we have a microphone going there. All right.
Yes, very nice result. I'm wondering if you could comment on how this will possibly influence future design of task and motion planning algorithms.
That's a very interesting question. This may have some applicability for if you're in charge of the dynamics and you have the ability to manipulate how the systems fit together. If you can prove that a system will be feasible, then maybe it's okay to hand it off to a sample-based or a more practical planner at that point. In terms of directly applying it, I'm not sure that it's at a stage where it can be applied. But yeah, that's a very interesting question. I'll have to think about it more.
Okay, do we have another question from the audience? We do have another question, and I cannot see very well people at the back because of the lighting. Thank you.
So if I understand correctly, you've shown that the plan existence problem is decidable for PTAMP. Does the same approach work to show that there exists or does not exist or does not exist a plan with some fixed path length or cost?
This is just a reachability approach. In fact, the dynamics are completely integrated out, so it's sort of oblivious to the path costs. It's possible that maybe it could be modified to account for path costs, but that seems like a much harder problem.
Quick question here. You talked about low-dimension manifold and perturbation. Do you have any insight into what are the physical configurations or something geometric where these low-dimensional manifolds can arise? What situation happens? It might happen.
Well, one example is if you have a robot manipulating an object, and you want the robot to be touching the object at all points during the manipulation. In that case, we're necessarily on a codimension 1 manifold because we lost a degree of freedom. And it's tough to reason on a low-dimensional manifold. So if we just increase the volume of the manifold, it makes it much easier to do these decompositions.
Okay. While the next speaker sets up, we can take one more question, and I believe there was a question at the back. Yes?
So the perturbation method that you present seems very similar to delta decidability for verification in hybrid automata or hybrid systems. Can you comment on that? So how does it relate to delta decidability, where you can get the answer correctly for false, but you get only a delta approximation for correctness?
I'll have to think about it a little bit more. I haven't made that connection yet.
Okay. All right. Thank you very much.